Well, I'm back. Still in my house. It's still Wednesday. Gonna try to show you how to do some actual statistical comparisons for our experiment. Uh, if the morning is any indication on how this will go, I will be interrupted 7,000 times. So, get your counters out, I guess. Alright, I gotta get my head right. I'm gonna be looking between two screens here, so it's gonna seem like I'm looking away from time to time. But I think it'll be worth it. We'll see. So I played around with some code to try to visualize our data and do some statistical analysis, and I think I got it working, so I'm going to show you what it is. First thing, we're going to recreate what we've already done. And so we've set our working directory. We're going to use the ggplot2 library, create a container called all the data. We're going to read in all of the data in our working directory. And if you recall from the last video, we put a little tag at the beginning of the data files, C for control and E for evolution. So I'm going to submit these commands, and that will bring in all of our data into one big data frame. I slayed 7,722 aliens right here, and we've recorded 61 variables of information about them. So that's a very large data set for a rather simple experiment. And now, it's hard for me to see my cursor. What we've been doing is trying to visualize the evolution of this dominance trait. And recall, dominance is the order in which the aliens enter into the field of play at the beginning of each generation. Highest value of dominance goes first. And our hypothesis is that under normal conditions of play with the ship that I chose, dominance is under selection. And the way we constructed our experiment is to test a particular prediction of that hypothesis. And that is, if it's under selection, dominance will change. And if we turn selection off by deactivating the fitness functions, dominance won't change. It'll stay the same. And so I ran 6 replicates of that experiment, 3 under control conditions where fitness functions were deactivated, random mating, and 3 where the fitness functions were on. And when we look at the data, we get scatter plots that look like this. Now every point here is an alien, and you can see up the top are 3 control replicates. It sure looks like dominance isn't changing. The mean value of dominance isn't changing, but statistically we need to evaluate that. And then when we have E, the selection condition E, where the fitness functions are turned on, it looks like to some degree or another, and a magnitude of the change varies, but in all cases, the mean of dominance tends to go down. Now, the first thing I'm going to show you is we should probably actually plot the means for each of these conditions. And so I'm going to go over here, and I'm going to show you how we can use this library called Plier to calculate some averages and get some summary statistics. So it's very likely at this point you're going to have to go to Packages, Install, and I want you to search for dplyr. So DPLYR. All right, and there it is. And if you click on it and you hit Install with an install dependent, it'll install that library for you. I've already done it. And then you go up here and you put another library command in, and you run that, and you should be ready to go. And so what I'm going to do is I'm going to go up here, and I'm going to start annotating our code. And so if you put in number signs at the beginning of these commands, it's like comments and it won't run it. And this is just good programming hygiene. And so this little chunk of code here reads in all the CSV files from our working directory. Now I'm going to do a new thing. I'm going to calculate the averages of dominance for each generation. And I'm going to do it for each file. And then down here, of course, the ggplot command. That visualizes our data. So here I want to calculate some averages and actually plot the averages on our graph, just to show you. I've been saying, hey, it looks like the average goes down. Well, we need to actually quantify that. So this code takes advantage of that plier library. So I'm going to create, again, I'm really bad at naming things. I'm going to create a new object called averages. It's a new data frame. And it's going to rely on this data called all the data. And then I'm going to do this little doodad here. I don't know what this is called, but this is what you do with this plier thing. It's essentially saying I'm going to manipulate this data frame, all the data, and I'm going to group underscore by, and then open some parentheses. And I want to group by two variables, file and generation. And also selection. And so this is a little bit redundant, but I'm going to say grouped by file, generation, and selection. So all of the unique combinations of these three variables. And I'm going to put this little continuation pipe command here. And then I'm going to say summarize. And I'm going to say the new variable called mean dominance is equal to the mean, and now this is a command of the variable called dominance. And I don't think I need to do that. NARM equals T, but it's a good, I don't think I need to do it. Okay. And so this is saying I need to make a new thing called averages. And I'm assigning to that thing, and this is a plier command that says, hey, look in the data frame all the data, and then group all of that stuff by these three variables. And then when you're done doing that, calculate for each of those unique combinations the mean of the value dominance and call it mean dominance. So that probably seems confusing, and you're probably like, this is what's happening. I hate this. Don't worry, just do this. And then when you do it, look, we got a new thing over here called averages. Let's go look at that. I click on it, and it's like, here's this file. And for this particular file, its selection type is C. For generation 1, the mean dominance was -1. And for generation 2, it was -1. For generation 2, or for 1, it was -1, and so forth. All the way through to generation 18. And then the next file, generation 0, and so forth. So we just calculated the average dominance for each generation for each of our 6 data files. Very good. For doing this is the kind of thing where it would have been faster for me to do this for one file and one generation in Excel, but as soon as you have these extra pieces in your data files, this code becomes very, very powerful. So I've calculated those averages. Now let's use that information in our visualization. So I'm going to go down here and I'm adding one command here. I want to add a line to my graph that is the averages that we've just calculated. And so what I'm going to do is I'm going to say the data equals our new thing that we made called averages. And I'm going to go ahead and add a line here. And for that aesthetic, for that particular part of the graph, it'll be largely the same as the aesthetic I set. I'm pointing to it like you can friggin' see. That's funny. The largely the same as the aesthetic we set up here for the main plot. However, I'm going to go outside the aesthetic parentheses here, and I'm going to tell it, I just want the mean line. I don't want it to be red or blue. I just want it to be black. And so I just want a black line that says what the average is for each generation. And then I add a plus sign here. So so this is what our plot looked like. It was just like red blobs, blue blobs. And that's just all of the aliens. I want to know what the averages are doing. And so I've calculated those averages. And note, this is really cool because with ggplot, I can make my main plot use one data set. And on the same graph, I can plot data from a different data set as long as it's structured similarly. And so now when I hit Command Enter, it says dominance not found. And that's because, remember, we called it mean underscore dominance in average. See, if I go to averages, I changed the variable name because it's averages. Now, and people are still texting me. Amazon stuff's coming. That's fun. So now, this is what the plot used to look like. And then I added the averages. And so if we zoom in here so you can see it a little better, the black line on each of those plots shows what the population average is doing over time. That's pretty cool, right? I like that. Now, I mean, it's a little easier now to see, oh boy, yeah, the average dominance when selection is turned on sure is going down, but we're still left with this subjective, sure looks like it's going down, and that's not how we do science. We have an entire field of science called statistics that allows us to infer whether the pattern we have observed could have happened by chance or not. And so that's the next part of this video. So I'm going to hit save there. So we've added a little bit more information to our plot. That's kind of fun. But now we have to sort of figure out a way, are these differences we've observed, this pattern that we've observed, could we have observed that by chance? And what is the probability we could have observed it by chance? Right? That's the crux of our hypothesis. Our prediction is that our two conditions will look different, and one, the dominance will have changed, and under the control condition, the dominance won't change. And we have a pattern that visually conforms to that prediction. Does it statistically conform to that prediction? Now, here's the thing. There's actually quite a few different ways that we can analyze these data. And I think I'm going to start with the simplest way first, and then I'll just sort of feed you. There's actually lots of options in terms of how to analyze the data. And it varies depending on the sort of level of sophistication that you're willing to adopt in terms of your analysis. So let's do, I'm gonna go ahead and I'm going to do something here. I'm going to go back to my thing. I'm going to say, okay, let's do a statistical analysis. And so I think the simplest way to do this, if you haven't taken Stats 250 in a while and things, is let's just focus on the outcome of the experiment. What happened at the end in generation 18? Because if our hypothesis is true, then when evolution is turned on, the average dominance at the end of the experiment should be significantly different from the average dominance of the control condition. And so that's leaving a lot of data on the table, but it's sort of an easy way to get to a statistical analysis. So what we need to know is, what was the average dominance value for each replicate at the end of the experiment? And so let's figure out a way to calculate that. So I'm going back to the code that I got to work earlier in the day. And the first thing that I'm going to do is I'm going to subset the data. I'm going to say, okay, I'm only interested in the generation 18 data. So I'm going to create a new data frame called Gen 18. And to that, I'm going to assign a subset. And that subset is going to be of all the data, that thing that we created. Okay? And I'm going to say generation. I'm going to say Gen 18 is a subset of all the data, comma, generation equals 18. So here's the thing. When we are using this as a logical operator and not an assignment, so if I wanted to say the value of generation is equal to 18, I would just use one equal sign. If I'm asking whether or not the value of generation is equal to 18, I use two equal signs. So this is the logical operator. That's a very common mistake that I make all the time. I forget that. So when I run this, I get a new thing called Gen 18. That has only 403 observations of 61 variables in it. And if you look at it, it's all of our data, but you go over here to generation, but it's only from that last generation, generation 18 of the experiment. Hoping people are keeping up with me on this. And hit save. And now I'm going to do the same kind of thing that I did up here. Okay, with this plier command. I want to calculate the averages of dominance, but I'm not really worried about generation anymore because it's only generation 18 that I'm worried about, right? So I'm going to do this exact same thing. And in fact, what I'm going to do, I'm going to go up here, I'm going to copy this stuff, and then I'm going to modify it. Programming is cutting and pasting and modifying most of the time. For here, I'm going to call this new thing Gen 18 averages. And instead of doing all the data here, I'm going to just look at the data set Gen 18. And I'm going to group by file. That's important. And selection. But now I don't need generation anymore because I'm only looking at one generation. And I'm going to summarize the mean of the dominance value, and I'm going to call it mean dominance. Okay? And so when I do this, I get a thing called Gen 18 averages, and it's 6 observations of 3 variables. And if we look at that, it is the file that it came from, the value of selection, C or E, and the mean dominance. And so we can see that for the selection value C, we get at the end of the experiment, our average dominance values are negative 0.776, negative 0.134, and 1.25. And when evolution is turned on, the E condition here, our mean dominance values end up being, at the end, generation 18, negative 4.6, negative 9.8, and negative 13.1-ish. So again, reasonably different values, but we need to do a statistical analysis to determine if they are significantly different or not. And I don't really like doing this when I only have 3 replicates of each condition. I strongly advise you to do 5 replicates of each condition because you get what's more statistical power. But we'll do this here. How would you compare? I've got 3 observations here and 3 observations here. Are these 2 groups statistically different? You can just do a straight up linear model. A t-test or an analysis of variance and t-test are mathematically equivalent for this data structure. Okay. Are these 3 significantly different from these 3? So let's do that. Like I said, this is the most simple way I could think of to analyze this particular set of data. And so now what we're going to do is a simple statistical test of that. And so we've got, let's call this test underscore dominance. Okay, that's a new object. And this is going to be a different kind of object. And we're going to do LM. LM stands for linear model. So we're going to assign to this object test dominance the results of a linear model analysis. LM, I don't think you're going to have to install any packages. I think LM comes with base R. You'll have to let me know if that's not the case. LM, and now we need to tell it what data set do we want to use. Well, we want to use Gen 18 averages. Okay? I said okay again. So difficult not to do that. And then we want to tell it what formula to use. Formula equals, and in this case, it's very simple. So for a one-way comparison like this, we're just going to say, well, I just want to double check. We called it mean dominance, right? We think that mean dominance depends on the value of selection. And so we just type mean underscore dominance. And then here I'm going to give myself a little more room here. And then this tilde thing means depends on or is a function of, we'll just type selection. And what I'm going to do, I'm going to hit a little enter here so that you can kind of see it. So this little thing, when we run this, will create some new thing called test dominance. All right. Now, if I just type test dominance, it gives you the coefficients of this particular linear model. But that's not the entirety of what we want. What we want to do is get the summary of test dominance. So when we run that command, and you scroll up here in the console, you get the call of the mod. So this is just like here's the command you use: the call, the residuals. Don't worry too much. This is not a stats class, so we're not going to worry too much about residuals. The coefficients of the model. So let's interpret that. So you have 2 pieces of the model. You have the intercept and then the value for, the variable. So in this case, it's selection. Don't worry about this E right now. What we really care about is this asterisk and this p-value. So this is our t-test statistic. This says, given this variance structure, the probability of observing a difference in means between these 2 groups just by chance, when no difference actually exists and it's just random chance, is 0.02. And our p-value, this is our p-value, is less than 0.05. And so by convention, we usually say the probability of observing this difference by chance is very low. Therefore, this result is consistent with our hypothesis that when evolution is turned on, dominance is under selection. The process of selection is causing dominance, in this case, to go down. Okay. Coincidentally, if you look at this, this tells you the effect of the difference between the two means, between control and the evolution, is negative 9.25-ish. And then the standard error is that. But if you look at this difference, negative 9.25, and we go back to our Gen 18 averages, if you calculate this average and this average, the difference between the two of them will be about negative 9 point whatever we said that was going to be. Can't remember. 9.25. Okay. So that tells us that those two groups of means with this very rudimentary t-test are significantly different from each other. And so that's good. But what if we wanted to actually calculate that and visualize it? Right. So now the endpoints are significantly different, but our graph is really more about the dynamics of the pattern. So we should calculate what those averages actually are. What is the average for our whole experiment? And so I'm going to create a new thing called bar averages. And that's going to get this whole thing again, and we're going to do group by again. But in this case, I'm just going to group by our experimental variable selection. And I'm going to do something a little bit different here. Bear with me. I'm going to summarize, and I want mean dominance to be equal to the mean of dominance, and I want to get another thing. I'm going to hit a comma here. I want the standard deviation to be equal to the standard deviation, so that's SD of dominance. So now I'm calculating both the mean and standard deviation of control and evolution replicates. And so if I highlight this and I go to bar averages, what we've got here is the control replicates, their average dominance at the end of the experiment was 0.09, and the evolution replicates, their average dominance at the end was negative 9.4. And the standard deviations of these two things were 1.79 and 3.78. And now I'm going to do a little manipulation here. And I'm going to create a new variable called standard error. And I'm going to say, hey, go look at this data frame called bar averages and the value called SD, and divide it by the square root. In this case, our sample size is 3 replicates each. So standard error is the standard deviation divided by the square root of the sample size. And so now I have the means, the treatment means, and an estimate of their standard error, which we will use for error bars in a traditional bar graph. And so now, if we want to visualize a bar graph, I'm going to go ahead and paste this in so you don't have to watch me type. In this case, I am going to make a bar graph. So in this case, I'm calling ggplot. I'm calling the data frame bar averages. We just did that. The aesthetic is on the x-axis. I want the category of our experiment, which is the variable selection. I'm going to do this so that you can see what I'm doing here. So x-axis is selection. The y value, the actual value, is the mean of the dominance. And here's this weird thing. Normally, when I want these things to be a different color, we would say color. But when we're doing bars and big shapes, it's actually fill you want. So I want each value of selection to be a different color, filled with a different color. And so I'm just going to show you what this looks like, just like this. Okay? So we're going to have the value of mean dominance on the y-axis. And we're going to have two categories, C and E, for selection. Okay? And then, if we want a bar graph, we're going to use the geom bar. And for reasons I don't want to explain, the stat is equal to identity. So don't worry about that right now, just do it. And if we plot all of that, we get our bar graph. And here's the thing, it looks funny because the average value for the control condition was so close to 0. If you recall, the average value was 0.09. And remember, our hypothesis predicts that the average value of dominance won't change, and it starts at 0. So it didn't change very much. But this looks weird, and our other value is -9. And so what I want to do is add some error bars. And that's why I took you through that thing where we calculated the standard error. There's this thing called geom error bar. And what I do is I say the aesthetic for that is the y minimum is the value of mean dominance minus the standard error. And the maximum is mean dominance plus the standard error. And then I'm going to go ahead and do that. And then you can control the width and the sort of offset of this. So then when we do all of this together, that is what our outcome looks like at generation 18. Under control conditions, it's a mean of effectively 0 with the standard error of around 1. And under conditions where evolution was turned on, it's a mean of around -9 with a standard error of around 1.5. And then we would put this figure and maybe potentially the dynamics figure into your report, and you would say these results are significantly different, and that supports the predictions of our hypothesis. The null hypothesis is that these two conditions would not have significantly different outcomes, and that is clearly not the case. And the probability of observing this difference, a difference of this size, purely by chance was 0.02. Now, keep in mind that this analysis leaves a lot of data on the table. We just threw out all of the data from generations 0 through 17. And I'll show you how to deal with that in the next video. Okay, bye.